So this is number theory, lecture 2. And I will start lecture 2 by reviewing what I did in lecture 1. And I emphasize the fact that everything is in the book, which is legible and on course materials on Blackboard, at least the first 2 chapters, which will get us through most of this semester. So I started off by stating the minimum principle, which is the basic axiom we use everywhere in number theory, which says that every non-empty set of non-negative integers contains a minimum or a smallest element. And the minimum principle was all we needed to prove the first theorem, which was the division algorithm. Which says let A and B be integers, and B is positive, means strictly greater than or equal to 1. There exist, this is an existence statement, unique, so it's also a uniqueness statement, unique integers Q and R such that A is BQ plus R, and R is an integer which is at most B minus 1 and non-negative. And we call Q the quotient, and we call R the remainder when you divide A by B. So for example, if A is, I don't know, 273 and B is 58, what is the quotient and what is the remainder? So you can almost sort of guess in your head what the quotient has to be. B is about 60 and A is a little bit bigger than 240. So the quotient is probably 4. What's 4 times 58? 4 times 50 is 200, 232, 32 plus 41. So this is my quotient. And if I did my arithmetic right, this was my remainder. Right? So that's the division algorithm. It just says that when they taught you in elementary school or wherever about long division, it really was an algorithm that always worked. You could always divide one integer by any positive integer and get a unique quotient and a unique remainder. All right. Any questions about that? Another consequence of the minimum principle is what is called the principle of mathematical induction. Which says the following: suppose you have some statement about the integers, so that's S of n, be a proposition or a statement or an assertion about the integer n. If, well, it doesn't really matter where you start, if S of n naught is true, so usually the starting point n naught is 0 or 1, and if the truth of S of n implies that S of n plus 1 is true, the truth of S of n plus 1, then S of n is true for all n greater than or equal to n naught. So this is really a very powerful method of reasoning in mathematics. I'll give it a star. If the statement is true, if f of S of n is true for 1, and whenever it's true for 1, it's true for 2, true for 2, true for 3, and so forth, then it's true for all integers. And we use that to prove that every positive integer has a unique binary representation. So a binary representation which is also called a two-adic representation, says that every integer, positive integer n, can be written as a sum of distinct powers of 2 in a unique way. So I'll pick a number at random, 491. I want to write 491 as a sum of distinct powers of 2. So the method, the algorithm that always works, is to pick at every step the largest power of 2 that you can. So what are the powers of 2? 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. Well, if you look at these, the largest power of 2, not bigger than 491, is 256. So I'll choose 256, and 491 is 256 plus what? I think it's 256 plus, let's see if I can do my arithmetic right, 235. Yeah, that looks right. And what about 235? Well, the largest power of 2, not bigger than 235, is 128. So this is 256 plus 128 plus how much? 107, I think. So this is a power of 2, and here I have 107. The largest power of 2, no bigger than 107, is 64. So this is 256 plus 128 plus 64. And 107 is 64 plus 43. The largest power of 2, no bigger than 43, is 32. This is 256 plus 128 plus 64 plus 32 plus 11. And 11 is 8 plus 3, which is 2 plus 1. So I have my dyadic, or my two-adic representation of 491. Let me write it as a sum of increasing powers of 2. 2 to the 0 plus 2 to the first power plus 2 cubed plus 2 to the 5th plus 2 to the 6th plus 2 to the 7th. That's this guy, plus 2 to the 8th. So here I've written 491 as a sum of powers of 2, and it requires quite a few of them. Actually, it requires 7 powers of 2, which is this happenstance. You don't know what it's going to be until you solve the problem. Okay. Any questions about this? So these two-adic representations of numbers are very important in many places, especially in computer science. And in computer science, one often considers other ways of writing numbers. And there's a general theorem which says the following. So now we start the material that is new to lecture 2. So this is the first new theorem of the day, that m be an integer, any integer at least 2. So we fix m. So every positive integer n has a unique, what is called m-adic representation. So n is a sum of powers of m with certain coefficients where these are fixed powers of m. This is m to the 0, which is 1, a0 times m to the 0, m squared, m cubed up to some m to the k, where these coefficients, a sub I, are integers between 0 and m minus 1 for all I going from 0, 1 up to k. And this last coefficient is actually positive. A sub k is greater than or equal to 1. So this is the m-adic representation of a number. And the simplest example we already looked at, m is at least 2. If you take m equal 2, then the coefficients a sub I are between 0 and 2 minus 1, which is 1. That just means ai equals 0 or 1 for all I. That's exactly what we saw with the two-adic representation. You had powers of 2, which meant the coefficients of the power of 2 was either 0 or 1. Let's look at an example of a 3-adic. Suppose, let's see, what was the number I used before? 491. Suppose n is 491. So I want to write n as a sum of a0 plus a1 times 3, a2 times 3 squared, a3 times 3 cubed, and so forth, up to some a sub k, 3 to the k. So I have to know what are the powers of 3. Well, we have 3 to the 0 is 1. 3 to the first power is 3. 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81. 3 to the fifth is 243. 3 to the sixth is 729, and so forth. Now, I'm looking at the number 491. So it's clear that I can't use any power of 3, which is like 729 or bigger. That's too big. In fact, 491 is between 3 to the fifth and 3 to the sixth. So let me choose the largest power of 3, not bigger than 491. I'm going to write 491 as some multiple of 243. And the largest multiple I can pick is 2. Right? 2 times, right? Because let's just note 2 times 243 is 486. Oh, that's nice. 491 minus 486 is 5. So 491 is 2 times 243 plus 5. What is 5? 5 is 3 plus 2. That's 1 times 3 and 2 times 1. So here I have my three-adic representation. 491 is 2 times 3 to the 0 plus 1 times 3 to the first power plus 2 times 3 to the fifth power. Or if I wanted to look like this, I'm just plotting zeros. 2 times 3 to the 0, 1 times 3 to the first power, 0 times 3 squared, 0 times 3 cubed, 0 times 3 to the fourth, and 2 times 3 to the fifth. So here you can see all the powers of 3 up to the fifth power of 3. But these powers of 3 have coefficient 0, and usually we don't bother to write them. We just write everything like write the positive powers of 3 that occur. So this is the three-adic representation of the number. Let's look at another example. These are kind of fun. Suppose I want to look at the four-adic representation of 491. So we have to look at the powers of 4. What are the powers of 4? 4 to the 0 is 1. 4 to the first power is 4. 4 squared is 16. 4 cubed is 64. 4 to the fourth is 128. 4 to the fifth is 512. Well, this is already too big compared to 491. So 491, the largest power of 4, no bigger than 491, is 128. And how many 128s would go into 491? I think 3 of them. Plus 3 times 128. Let me do my arithmetic just so everyone can see it. 128 times 3 is 384. 491 minus 384 is 107. What's the largest power of 4, no bigger than 107? It's 64. So this is 3. Oh, I'm sorry. I made a mistake here. Made a mistake. The powers of 4, 1, 4, 16, 64. 4 times 64 is 256. 4 to the fourth is 256. And 4 to the fifth is 1012. So this is all wrong. I'm always happy when I make a mistake. Of course, then I get to correct it. So the highest power of 4, no bigger than 491, is 256. And that only goes in once. So 491 is 256. And what is 491 minus 256? 11 take away 6 is 5. 8 take away 5 is 3, is 235. So this is 1 times 256. The largest power of 4, no bigger than 235, is 64. And I think 3 times 64 is no bigger than 235. Let's see. 64 times 3 is 192. So 235 minus 192 is 43. Largest power of 4, no bigger than 43, is 16, and 16 goes into 43 twice. So this is 1 times 256 plus 3 times 64 plus 3 times, oh, no, not 3 times 16, that's 48. 2 times 16, that's 32 plus 11. So this is 1 times 256 plus 3 times 64 plus 2 times 16. 11 is 2 times 4, that's 8 plus 3, which is 3 times 1. So let me write this in terms of increasing powers of 4, because this is my 4-adic representation. 491 is 3 times 4 to the 0, plus 2 times 4 to the first power, plus 2 times 4 squared, plus 3 times 4 cubed, plus 1 times 4 to the 4th. So if I did my arithmetic correctly, this is the 4-adic representation of 491. All right. So let me give you a problem to do right now. Compute the 5-adic representation of 491. So you have to know the powers of 5. 5 to the 0 is 1. 5 to the first power is 5. 5 squared is 25. 5 cubed is 125. 5 to the 4th is 625, and so on. 5 to the 5th is 3125, which is already way too big. So calculate the 5-adic representation of 491, and I'll give you a couple of seconds to work that out. In the chat, someone asked whether the p-adic representation is related to the m-adic representation. And the p-adic representation is the m-adic representation when m is a prime p. So in the special case where m is a prime, it's called a p-adic representation. So the 5-adic representation is the m-adic representation with m equal 5, and also the p-adic representation with p equal 5. But you can do these representations of numbers to base m, whether or not m is a prime. It just has to, it can be any integer, at least 2. So can someone tell me what this 5-adic representation is? Let's see. The largest power of 5 you can do is 125.
It would be 491. 491 equals 3 times 125 plus 116.
Plus what?
Plus 116.
Okay, that's the first step.
And then right after is 3 times 125. And then I believe it's going to be what's that?
The highest power of 5 up to 116 is 25. So you're going to use some multiples of 25. And
Is it 4 times 25?
right, that's 100. So that leaves us 16.
Plus 16. And then it'll be the same thing. And then the next step will be 3 times 5 plus 1.
Okay, so that's it. That's exactly right. So this is 1 times 5 to the 0, plus 3 times 5 to the first power, plus 4 times 5 squared, plus 3 times 5 cubed. And here we have 491 as a sum of powers of 5. And the coefficients are integers 1, 2, 3, or 4. At most 5 minus 1 or 4. So that's the 5-adic representation. So sometimes people say, and we have some problems on the exam that aren't proofs, that are just calculations. So will be a typical exam problem. I'll give you a number and say, write the M-matic representation for some M. Right? It's a very nice exercise in arithmetic. Arithmetic, of course, is just another name for number theory. Studying the integers. Okay. Now, there's always a question in mathematics of what language do we use? And it's very useful in number theory to use the language of algebra, and in particular, group theory. So I have to define what is a group. So, with the integers, you can add them. 3 plus 4 is 7. And you can multiply them. 3 times 4 is 7. You cannot necessarily divide them. 3 divided by 4 is not an integer. But if you looked at the rational numbers, the fractions, then you can divide 3 by 4. But addition, multiplication, these are examples of what are called binary operations. So a binary operation on a set X is just a function that assigns an element of X to every ordered pair of elements of X. For example, if X is the integers, we could have the operation of addition. 3 plus 4 equals 7. So to the ordered pair of numbers 3, 4, we assign this number 7, 3 plus 4. Or if we took X to be the real numbers with the operation of addition, we could say that 5 plus, I don't know, the number 5 plus the number square root of 2 is 5 plus the square root of 2, right? That is, you can add pairs of real numbers. You can multiply pairs of real numbers, and so forth. The same with rationals and complex numbers. So binary operation is simply a function that assigns some number, some value to every pair of elements of your set. So let me call my set G. Let G be a set with a binary operation. And usually it's either addition or multiplication. And just so I can deal with both of them at the same time, I'm going to call it like this asterisk. So X times Y, X plus Y, this is the binary operation. So, so G is a group. What is a group? A group is a set with some binary operation where the binary operation satisfies 3 properties. So G is a group if the binary operation plus or times, or called star, satisfies the following. First of all, it's what is called associative. So x times y times z is the same as x times y times z. And again, you can check that in the integers or in the reals or in the rationals, both addition and multiplication satisfy this. So for example, 3 plus 4 plus 9 is what? 16, which is the same as 3 plus 4 plus 9. This is associative. Or 3 times 4 times 9, what is that? That's 12 times 9, that's 108. That's the same as 3 times 36, which is 3 times 4 times 9. So 3 times 4 times 9 is the same as 3 times 4 times 9. 3 plus 4 plus 9 is the same as 3 plus 4 plus 9. So the addition and multiplication you're familiar with are both associative. Second property a group has to satisfy is existence of an identity element, E, in the group. And the identity element satisfies the property that x times E and E times x are always equal to x for all x in the group. So for example, if we take the rational numbers with addition, the identity element is the number 0. Plus x plus 0 and 0 plus x is always equal to x. If we take the rational numbers with multiplication, there's an identity, which is just the number 1. X times 1 and 1 times x is equal to x. So the second property a group has to satisfy is that it contains an identity element. And the third property is existence of inverses. This says that for all elements x in the group, there exists an element y in the group such that x times y and y times x are both equal to the identity. So if I take as my example the integers or the rationals q, or the real numbers or the complex numbers with addition, every element has a negative. 3 plus minus 3 and minus 3 plus 3 is 0. So there's an additive inverse in the integers for every element in the integers. Now we come to a little tricky point. What about multiplication? See, just 1 second. Suppose I take z with multiplication. If I take x equal to 3, see, 3 times, so the identity is 1 under multiplication. 3 times y equal 1 is impossible in z. Right? There's no multiplicative inverse in the integers for the number 3. So Z with multiplication is not a group. Suppose I take the rational numbers. If I take x equal 3, well, then I can take y equal to a third. Because 3 times a third, or a third times 3, is equal to 1. So in the rationals, 3 has a multiplicative inverse. Suppose I take x equals 0. 0 times y is always 0. It's never equal to 1. So 0 has no multiplicative inverse. So Q with multiplication is not a group. But the only element of Q that fails to have a multiplicative inverse is 0. So suppose
I'm sorry, Professor. It's hard for me to understand the writing. It's a little bit.
Right, well, that's what I say. My writing is my writing, and I can't change it. But that's why we have a book. Everything is in the book, and the book is printed. Right, so you can always understand the book. Right, and the book is really what you need to study, more than the notes or anything else. So suppose we let Q star times be the rational numbers with 0 taken away. So this is the non-zero rational numbers. The non-zero rational numbers. This is a multiplicative group. If you take any rational number, P over Q different from 0, then Y equal Q over P is a perfectly good rational number. And XY is PQ times QP is equal to 1. So the rational numbers with 0 removed is a multiplicative group. So if you have a set with a binary operation that is associative, has an inverse in every element, so it has an identity and every element has an inverse, it's a group. There's one other property a group might satisfy, but not necessarily. The group G is called abelian or commutative. They mean the same thing. If x times y equals y times x for all x and y in the group. So the order of the binary operation is not important. And the most important example is the integer z. With addition. So the integers that we know and love form an additive abelian group that is commutative, right? It's an additive abelian group. It's harder to find examples of groups that are not abelian, but here's one that you might recognize. Suppose I call it, it has this strange name, SL2R, let's say. So this is all 2 by 2 matrices, A, B, C, D, with the determinant AD minus BC equal 1. So this is a multiplicative group. with ordinary matrix multiplication. The identity matrix, the identity element, is just 1, 0, 0, 1. And if you take X to be the matrix A, B, C, D, the inverse is D minus B minus CA. But this is not a commutative group. For example, if I take 1, 1, 0, 1, I'm just making up two matrices at random. 1, 2, 3, 0. Let's see what this is if I multiply these two matrices together. I think linear algebra is a prerequisite for number theory, so you should have seen matrices. But if you haven't, we're not really going to use them very much, and hardly at all in this class. But what is the product of these two matrices? This is 3, 3, 2, 0. What happens if I multiply in the reverse order? 1, 3, 2, 0, 1, 1, 0, 1. This is 1, 2, 4, 2. These two matrices are not at all alike, they're different. So if I called this X and this Y, this is X times Y. This is YX, this is Y times X, and they're completely different. So this group of 2 by 2 matrices that have determinant 1 is an example of a non-abelian group. But again, if you're not familiar with matrices, that's fine, because we don't really use them in this class. Okay, so I just defined a group. What is a subgroup? So let G be a group with identity element E, a subset H of G is called a subgroup of G. If first of all, it contains the identity, and second, if X and Y are in H, then X times Y is in H. And if X is in H, then X inverse is in H. So H is a group all by itself. So H is a group contained in the group G. So that's what a subgroup is. A subgroup of a group is a subset which, with the same operations as in G, is all by itself a group. And our fundamental group in number theory is the group of integers under addition. And I'm going to describe right now what are the subgroups of Z. So consider Z, which is an additive abelian group, a group with addition. By the way, what's the inverse of an element of Z? Take the number 3, the inverse is -3. The identity element is 0. The inverse of X is -X, because X plus minus X is X minus X is 0. Okay. Suppose I let H be the set of even integers. So 0, 2, 4, 6, -2, -4, -6. And just all the even integers, positive, negative, 0 is even. Any number divisible by 2. This is a subgroup. Because why is that? The sum of two even integers is even. If I take the number 2a and the number 2b, every even integer can be written as 2 times something. 2a plus 2b is 2 times a plus b. 2a plus minus 2a is 0. Minus 2a is 2 times minus a. So the set of even integers is a subgroup of the integers. 0 is even, it's divisible by 2. 1 is not even, 7 is not even, but if I take any two even integers, if I add and subtract them, I get something even. And we usually write the even integers as 2z. This is sort of standard notation. Any questions about any of this so far? So that d be any integer, right? D is in the set of integers. That dz be the set of all multiples of d. 0 times d, 1 times d, 2d, 3d, 4d. Then the negative multiples minus d minus 2d and so forth. dz is a subgroup of z. So if I have AD and BD, two multiples of D, and I add them, I get A plus B times D. And if I subtract them, I get A minus B times D. And 0 is 0 times D. So the set of multiples of D contains 0 and is closed under addition and subtraction. It's a subgroup. So for every integer D, I get a subgroup of D. Because if I look at the multiples of minus 2z, I take minus 2z. This is just all multiples of minus 2. This is the set of all minus 2 times x, and z, which is the same as 2 times minus x, and z. This is the same as just all multiples of 2. Because every multiple of minus 2 is also a multiple of 2. So we don't get any new subgroup by considering negative numbers. So the sets dz for d0, 1, 2, 3, the non-negative integers, are distinct subgroups of z. What are the other subgroups of z? What are the other subgroups of the integers? Well, the amazing fact is there are no others. These are, in fact, all subgroups of z. And this is a very important theorem, which I will prove right now. So I'll call this a big theorem. It really is very important. Let H be a subgroup of the integer z under addition there is a unique non-negative integer d such that H is exactly the subgroup of all multiples of D. So this is the big theorem. Every subgroup of the integers is of the form dz, multiples of D for some unique non-negative integer D. So the proof, let's prove it. Case 1. H just consists of the number 0. Well, the set consisting of the number 0 is a subgroup because it contains 0, it's closed under addition, it's closed under subtraction. This is a subgroup. And H is just the set of all multiples of 0. That is, choose D equals 0. So if H is the 0 subgroup, if H only contains the number 0, then the theorem is true with D equal to 0. Okay. Right. What's the second case? Well, if the first case is H contains only 0, the second case is H does not contain just 0. So if H is not just 0, that means that there exists an integer a in H different from 0. If a is positive, good. If a is negative, less than or equal to -1, then minus a is in H, because H is a subgroup, it contains the negative of each of its elements. But if a is negative, minus a is positive, and minus a is greater than or equal to 1. So in every case, the set H must contain some positive integers. So H contains positive integers. Suppose I let H plus be the set of all positive integers in H. So I just showed this is not the empty set. This is, again, is the symbol for the empty set, the set that contains nothing. So the set of positive integers in H is a non-empty set. And now we use the minimum principle. The minimum principle says that H plus contains a smallest element. Right? The minimum principle says every non-empty set of positive integers contains the smallest element. This is a non-empty set of positive integers. It contains the smallest element. I'll call it D. So D is an H. Now, H is a subgroup, which means it's closed under addition. Well, if D is in H, and H is closed under addition, D plus D is in H, which is 2D. So D plus 2D is in H, which is 3D. And continuing, I can just show by induction that KD is in H for all multiples, positive multiples of D for all k greater than or equal to 1. But if KD is an H, minus KD is also an H for all k greater than or equal to 1. If I write this as minus k, this says that all multiples of D are an H. For all k, positive, negative, or of course 0, if k is 0, 0 times D is 0 for all k and Z. Which means, if I look at the set of all multiples of D, they're all contained in the subgroup H. If D is any element of H, the set of all multiples of D is contained in H. And I choose D to be the smallest positive element in H. What I want to show is that, in fact, H is equal to DZ. There's nothing else in H. And how can we prove this? Well, let N be any element in H, any element. We have the division algorithm. By the division algorithm, I can write N as D times some quotient plus the remainder, where the remainder is between 0 and D minus 1. And then what do I know? N is in H. DQ is in H. H is closed under addition, subtraction. N minus DQ is in H. But N minus DQ is R. R is in H. But R is between 0 and D minus 1, right? D is the smallest positive. Remember, positive means greater than 1, greater than 0. D is the smallest positive integer in H. So R is strictly smaller than D. R is at most D minus 1. So R is not positive. That means R has to be 0. If R is 0, N is D times Q. So N is in DZ. So every element of H is contained in DZ. And I have DZ is contained in H, and H is contained in DZ. Two sets are equal if each is a subset of the other. So H is D times Z. And that is the end of the proof. So this is really important. This is one of the fundamental results in chapter 1 that we use everywhere in this course. And you have to know the statement of the theorem, and you have to spend a lot of time to understand the proof. Because I could easily ask you to prove this result on the first midterm exam. This is something that you absolutely and positively have to know. Any questions about this? Okay. Let's talk about a basic property of the integers, which is divisibility. We say that the integer D divides the integer A if A is DQ for some integer Q. So this means D divides A if in the division algorithm the remainder is 0. So for example, 7 divides 56 because 56 is 7 times 8. 7 divides 1001 because 1001 is 7 times what? Well, I don't know. Let's see. See if I'm correct. Let's see if 7 divides into 1001. This goes in 1, 30. 4 times 7 is 28. 2, 1, 3. Ah, perfect. Is 7 times 143. So 7 divides 101.
Professor, is that a 57? There.
It'd be 56. Thank you.
56.
7 does not divide 100 because 100 is not equal to 7 times q for any integer q. We're only working in the integers. We don't have the luxury of having fractions. 7 doesn't divide 100, but it does divide, it doesn't divide 101 even, but it does divide 1001. It's kind of surprising, actually. We're going to spend a lot of time studying prime numbers.
Professor, someone wrote on the comments that the Monday lecture is not available via YouTube.
No, I said not yet. I'm having some trouble uploading it. As soon as I can upload it, I will send out an email to everyone. It will get there eventually, but I'm going to try, well, we'll see. I'm going to try today, see if I can upload it to Blackboard. Yeah. You know, we had discussed that already today. So a prime number is a positive, sorry, not just positive. This is the definition of a prime number. Prime number is an integer p greater than or equal to 2, whose only positive divisors are 1 and p. So what are some examples of prime numbers? 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and so forth. Each of these numbers, every number is divisible by 1. Every number is divisible by itself. A number is prime, or if those are the only prime divisors. A number that's not prime is called composite. Composite number is a number has to be at least 2. Certainly every even number is composite. Okay. 15 is not composite because it's divisible by 3 and 5. 3 and 5 are divisors other than 1 and 15. So we're going to spend a lot of time studying prime numbers, but it's defined in terms of divisibility. So suppose we have integers a and b. The integer d is called a common divisor of a and b if d divides a And also, simultaneously, D divides B. By the way, for notation, instead of having to all the time write D divides A, I just write D, a vertical line A. So this means D divides A, this vertical line. So if I take, for example, A equal to 1,001, B equal to 42, 7 divides 1,001, 7 divides 42, right? I already did the calculation. 1,001 is 7 times 100.
9?
Sorry?
Was it 9?
No,
140.
1,001 is 7 times 143,
Yeah.
and 42 is 7 times 6. So 7 divides both 1,001 and 42. So 7 is a common divisor of these two integers. More generally, we can say D is a common divisor of any set of integers, A1, A2, A3, and so forth, if D divides AI for all I going from 1, 2, and 3. So if I take, for example, A1 to be 1,001, A2 to be 42, A3 to be 84, then 7 is a common divisor of these three numbers. 7 divides 1,001, 7 divides 42, 7 also divides 84. 7 is 12, 84 is 12 times 7. So 7 is a common divisor of these three numbers. And we say that integers A1, A2, well, come to that in a minute. Okay. Just as a little exercise right now, compute, well, forget that. Let me define the greatest common divisor of a set of integers. So D is the greatest common divisor of a set of integers, A1, A2, A3, and so forth. If, first of all, D is a common divisor of all of them, and second, if D prime is any other common divisor of A1, A2, and A3, then D prime divides D. So the greatest common divisor of a set of integers is, first of all, it's a common divisor of the integers. And it's divisible by every other common divisor. And both the number D and its negative would have that property. So I also want to say D is greater than or equal to 1. I want the greatest common divisor to be positive. And that makes it unique. So if I take the numbers, say, A1 equal to 54, A2 equal to 78. A3, well, just 54 and 78. So 2 is a common divisor of 54 and 78, because 54 is 2 times 27, 78 is 2 times 39. Three is a common divisor of 54 and 78, because 54 is 3 times 18, and 78 is 3 times 26. 6 is another common divisor. Fifty-four and 78. 54 is 6 times 9. 78 is 6 times 13. So here we have 3 common divisors of these two numbers. 6 is the biggest of these 3, and it's divisible by 2 and by 3. And in fact, 6 is the greatest common divisor of these numbers. So 6 is the GCD of 54 and 78. GCD stands for greatest common divisor. And the notation for the greatest common divisor of integers a1, a2, up to a sub k is just put those numbers in parentheses. So what we just proved is the GCD of 54 and 78 is equal to 6. Right? This is the greatest common divisor of 54 and 78 is equal to 6. So compute the GCD of 3003 and 1470. Yeah, let me pause for a minute and I'll give you a chance to do that. Anyone get a result? What is the GCD of these two numbers? Well, let's see, 3003 is 3 times.
I got 3.
Sorry, did you get a result?
Yeah, I got 3 times 1001, and then I got 3 times
Well, no, the
90.
GCD is a number, so just give me the answer.
Yeah, I got 3.
Sorry? 3?
3.
Let's see. So 3003 is 3 times 1001. 1001 I had factored before. This was 3 times 7 times 143. Actually, 143, I think, is 11 times 13. That's 3003. 1470. You said correctly, this is divisible by 3. This is 3. See, what does 3 into this go? This goes 4. Let me just do it over here. 3 into 1470. So that's 4, 4, 3,
490.
490. Okay, so that's 3 times 490, which is 3 times 49 times 10. And 49 is 7 times 7, 2 times 5. So it looks like both of these numbers are divisible by 21, right? 3003 is 21 times 143. And 1470 is 21 times 70. And these two numbers are relatively prime. They have no common factor. So it looks like the GCD of 3003, 1470 is actually 21. Oh, that's kind of interesting. So, yeah, someone put this on chat correctly. Thank you, Felix. Actually, when we start to use Maple, Maple will calculate the greatest common divisor of numbers in a microsecond. But it's important to be able to do it by hand for small numbers. Okay, well, maybe this is enough for today because I think there's a lot to think about and a lot of homework problems also to work on. I will try to get the videos posted as soon as I can. I'm also going to set up a couple of Zoom office hours in the next couple of days. Remember, Monday is Labor Day. There's no class, there's no lecture. So the next lecture is actually 1 week from today, next Wednesday. Right. Any questions before we quit for the morning?
Professor, can you show us how to use Maple? Because I never used this app before.
Right, so we haven't gotten to using it yet, and I'm going to set up a whole lecture on that. But at this point, it's important to learn how to do these arithmetical calculations by hand. If you do go to YouTube, in the Nathanson Math Lectures channel, there are, I have video lectures for Math 155 and 156, especially Math 156. And when I teach Math 156, I use Maple. So everything you need to know and much more about Maple, about how to use it, you can find right now on YouTube. But I'm going to set up a class in this number theory lectures on Maple also. But we don't need it just yet. And it really takes an hour or more if I'm going to start to explain it. The first step is actually to download it from the CUNY email. CUNY students get it for free, otherwise it's expensive. And it also has the activation code. There's like the secret code you need to type in to get Maple to run on your computer. And it's right there on the website where you download it from. Yeah.
But homework 1 is, we use Maple to do homework 1, or we can just do it on
No.
notebook?
There's no Maple on any of the homeworks.
Oh, okay.
No, not at all. Zero Maple. That's why we don't need it yet at all. And the homework comes from the book, and there's nothing in the book that uses Maple.
So we can just write it in our notebook and then take a picture and upload it?
Yeah, that's what you have to do. Yeah, you're not supposed to use Maple for the homework.
Okay.
No, you write it out, make the PDF, and upload it.
Okay.
Okay.
Oh, it has to be PDF.
That's the best way. because then you get it on one document. And it's easy to upload to Maple, and it's upload to Blackboard, and easy for me to grade.
Okay.
Yeah, the worst thing is to use your cell phone to take pictures of it page by page and upload it. It's, I mean, it works if you can't find a printer that will scan a handwritten document and turn it into a PDF file, but that's I mean, if you can't, and then you can use your camera, but it's better to upload a single PDF document. Okay, all. See you a week from today. Bye.
Thank you, Professor.
All right, thank you.